A reduced voltage starter is employed to decrease the starting inrush current. Even if a motor is designed for Y-start/delta run configurations, the starting current can be exceedingly high, especially when the motor is loaded. The reduced voltage starter mitigates this by applying a low voltage to the motor during startup, which diminishes the starting torque but also significantly reduces the starting current. If the motor shaft can be turned by hand while connected to the load, it indicates the motor isn't loaded. In such instances, a delta connection is viable. However, when the motor is loaded, a reduced voltage starter becomes necessary to curtail the starting current. The transformer in a reduced voltage starter setup is often tapped at approximately 65% of the line voltage during startup. This configuration lowers the starting current by diminishing the voltage applied to the motor as it begins to run. While this also reduces the starting torque, the reduction in starting current is proportionally greater, preventing the motor from drawing excessive current that could damage itself or its protective devices. Several alternative solutions exist. Firstly, utilizing a reduced voltage starter is often the optimal choice for applications requiring inrush current reduction and protection against excessive current draw. Secondly, a soft starter offers a solid-state alternative that gradually increases the voltage applied to the motor during the startup phase, thereby minimizing inrush current. Thirdly, employing a current-limiting reactor, an inductor connected in series with the motor, can restrict the amount of current flowing through the motor, thus reducing the starting current. When dealing with motor protection, several factors come into play. These involve understanding the motor's full load amperage, the inrush current during startup, and the coordination of protective devices like circuit breakers and overload relays. Properly sizing the conductors feeding the motor is also crucial to prevent overheating and voltage drop. NEC Article 430 covers motor circuits and protection, providing guidelines for selecting appropriate conductor sizes, overcurrent protection, and control circuit components. To understand the application better, it's important to consider the type of load the motor drives. For instance, a compressor often requires high starting torque due to the static pressure it must overcome. This can lead to significant inrush current. Additionally, the frequency of starts and stops can affect the motor's lifespan and the stress on the electrical system. Frequent starts can cause the motor to overheat due to the repeated inrush current. When troubleshooting motor starting problems, it's essential to systematically check various components. Firstly, verify the supply voltage to ensure it's within the motor's specified range. Secondly, inspect the motor's windings for any signs of insulation breakdown, which can be confirmed with a megameter. Thirdly, examine the starter components, including contactors, overload relays, and timers for proper operation and any signs of wear or damage. Fourthly, ensure all connections are tight and free from corrosion. Fifthly, analyze the control circuit to identify any issues with the starting sequence or control signals. Reduced voltage starting methods are beneficial because they alleviate stress on the electrical distribution system. High inrush currents can cause voltage dips that affect other equipment connected to the same system. By reducing the inrush current, reduced voltage starters minimize these voltage fluctuations and improve the overall stability of the electrical system. Various types of reduced voltage starters exist, including auto-transformer starters, part-winding starters, and reactor starters. Each type has its own advantages and disadvantages in terms of cost, complexity, and performance. Auto-transformer starters use a transformer to reduce the voltage applied to the motor during startup. Part-winding starters energize only a portion of the motor windings initially, reducing the inrush current. Reactor starters use inductors in series with the motor windings to limit the current. Selecting the appropriate reduced voltage starting method depends on the specific application requirements, including the motor size, load characteristics, and electrical system capacity. Factors to consider include the desired starting torque, the acceptable level of inrush current, and the available space for the starter. Motor insulation breakdown can be caused by several factors, including overheating, voltage surges, and contamination. Overheating can occur due to excessive load, inadequate ventilation, or frequent starts and stops. Voltage surges can be caused by lightning strikes or switching transients. Contamination can be caused by moisture, dirt, or chemicals. Regular motor maintenance, including visual inspections, insulation resistance testing, and winding temperature monitoring, can help prevent insulation breakdown and extend the motor's lifespan. When replacing a motor, it's important to select a motor with the appropriate horsepower, voltage, and frame size. The motor's service factor should also be considered, which indicates the motor's ability to handle occasional overloads. A higher service factor provides greater overload capacity. Additionally, it's essential to ensure that the motor is properly grounded to prevent electrical shock hazards. Grounding provides a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and energizing the circuit. NEC Article 250 covers grounding and bonding requirements. When working with electrical equipment, it's crucial to follow all safety precautions. Firstly, always de-energize the circuit before working on any electrical components. Secondly, use appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. Thirdly, verify that the circuit is de-energized using a voltage tester before touching any conductors. Fourthly, follow lockout/tagout procedures to prevent accidental re-energization of the circuit. Fifthly, be aware of the potential hazards associated with electricity and take appropriate precautions to avoid electrical shock. Regarding the specific situation, the repeated breaker trips suggest an ongoing issue beyond the breaker itself. Replacing the breaker without addressing the root cause is only a temporary solution. The dark windings and insulation breakdown indicate a motor problem that needs to be addressed. The reduced voltage starter setup should be carefully reviewed to ensure it's functioning correctly and is appropriate for the application. If the transformer is tapped at 65% of line voltage, it's important to verify that this voltage level is sufficient to start the motor under load without causing excessive current draw or stalling. It's also important to consider the motor's thermal overload protection. The overload relay should be sized to protect the motor from overheating due to sustained overloads. If the overload relay is set too high, it may not protect the motor adequately. The size 6 starters in the pre-manufactured square D starting cabinet are sized according to NEMA standards, which specifies horsepower ratings for different starter sizes at various voltages. It's essential to verify that the starter size is appropriate for the motor horsepower and voltage. The conductors feeding the motor must also be sized according to NEC Table 310.16, which specifies the allowable ampacity of conductors based on the size, insulation type, and ambient temperature. It's important to consider the ambient temperature when sizing conductors, as higher temperatures can reduce the conductor's ampacity. The current transformers, or CTs, on the center leg are used to monitor the motor current for the computer-based controller/diagnostic setup. These CT provide feedback on the motor's performance and can be used to detect abnormal conditions such as overloads or faults. The computer-based controller can then take appropriate action, such as tripping the breaker or shutting down the compressor. The mechanical interlocks between the starters are designed to prevent multiple starters from being energized simultaneously, which could cause a short circuit. These interlocks ensure that only one starter is energized at a time, preventing conflicting control signals. The timing relays in the starting cabinet are used to control the sequence of events during the starting process. These relays ensure that the motor starts smoothly and without excessive stress on the electrical system. The tapped-off thermal overload setup provides additional protection for the motor. This setup monitors the motor's temperature and trips the breaker if the temperature exceeds a certain threshold. This protects the motor from overheating due to sustained overloads or other abnormal conditions. When troubleshooting motor starting problems, it's important to use appropriate test equipment. A multimeter can be used to measure voltage, current, and resistance. An ammeter can be used to measure current flow. A megameter can be used to measure insulation resistance. A thermal imager can be used to detect hot spots in the motor windings or other electrical components. These tools can help identify the root cause of the problem and prevent future failures. In addition to the electrical aspects, It's also important to consider the mechanical aspects of the system. The compressor should be properly maintained and lubricated to prevent excessive friction and wear. The belts and pulleys should be aligned and in good condition. The cooling system should be functioning properly to prevent overheating. These mechanical factors can affect the motor's performance and lifespan. Food processing plant environment can also contribute to motor problems. The presence of moisture, chemicals, or other contaminants can accelerate insulation breakdown and corrosion. It's important to protect the motor from these environmental factors by using appropriate enclosures and sealing techniques. Regular cleaning and maintenance can also help prevent damage. The ammonia-based compressor presents a unique set of challenges due to the corrosive nature of ammonia. Special precautions must be taken to protect the motor and other electrical components from ammonia exposure. This may involve using special coatings or enclosures that are resistant to ammonia corrosion. It's also important to ensure that the ventilation system is adequate to remove any ammonia leaks or vapors. The ICF, or individually quick frozen, system requires precise temperature control. The motor driving the compressor must be reliable and efficient to maintain the desired temperature. Any motor failures can result in product spoilage and downtime. Therefore, it's essential to implement a robust motor protection system to prevent failures and ensure the system's reliability. In summary, addressing the root cause of the breaker trips requires a comprehensive approach that considers both the electrical and mechanical aspects of the system. The motor should be thoroughly inspected and tested to determine the extent of the damage. The reduced voltage starter setup should be carefully reviewed to ensure it's functioning correctly and is appropriate for the application. The overload protection should be sized to protect the motor from overheating. The conductors should be sized according to NEC requirements. The mechanical components should be properly maintained and lubricated. The environment should be protected from moisture, chemicals, and other contaminants. By addressing all of these factors, the reliability and lifespan of the motor can be significantly improved. This will help prevent future breaker trips and downtime, saving the customer time and money. Remember that electrical work should always be performed by qualified personnel who are familiar with the NEC and other applicable codes and standards. Safety should always be the top priority. By following these guidelines, you can ensure a safe and reliable electrical system.